All right, well, we'll go ahead and get started today. So, Maggie, is Corey down there?
He's not here yet, but I saw him yesterday and it seemed like he was coming.
Okay. All right, just making sure he's all right
I
then.
don't think upset if we don't wait.
What's that?
I don't think he'll be upset if we start without.
Right. Yeah, no, I was I was just wondering how he's doing. I haven't heard from him in a little while. All right, so we did chapter 7 and 8 last week, but we didn't quite finish chapter 8. And so I'd like to do that and talk about that and maybe demonstrate another one of the homework assignments for chapter 8. But there's already a question, when's chapter 8 due if we didn't quite finish it? I guess I can just make chapter 8 due along with chapter 9 today. So, I mean, not due today, but we're going to present chapter 9 today. So that one will be due next Friday. So maybe we could just make it be, this one is just chapter 7, and then next Friday will be chapter 8 and chapter 9. That sounds reasonable. So, chapter 8. We already did most of one of the homework assignments in chapter 8, and I'll do at least one more, so that there won't be much left anyway, hopefully. Alright, yeah, so we talked about sampling, that was chapter 8. And what I actually want to talk about the sample size selection first, and then go back and talk about the stratified sample one, because in order of difficulty, the sample size selection stuff is more straightforward. So I'm going to go towards the end. This is the last 3 slides, and then I'll do the 3 slides before that. So last week, as a refresher, we talked about calculating confidence interval and about a mean and about a proportion. Those were called, well, what were those called? Like when we come up with a estimate of the mean, I don't know. So maybe that was a bad question. Starting off today, but we have a bunch of different, not a bunch, but there were a few different point estimates that we talked about last time, and then we have the point estimate, and then I thought I turned this down already. The confidence interval is above and below that point estimate. There we go. Now it really is turned down. Okay. So the sample size selection is really a very similar problem, just working at it from the opposite direction. And so if we decide that this is coming into it saying, okay, if I have a certain value and I would like to predict it with a certain confidence level, so I come up with an alpha, what size of what sample size do I need in order to have the confidence interval be the width that I want it to be. So this kind of says a little better. Sometimes we prefer to predetermine our confidence interval and then calculate the sample size that we need. So instead of taking the sample first and figuring out what our confidence interval is, we decide this is what our confidence interval needs to be. So how big of a sample do we need in order to have a confidence interval that's that much? So if it's like a difference of proportion questions, if we decided that we wanted to be able to say with 90% confidence that maybe it was a pre-election proportion that's we wanted to be within 1 percentage point either way, then we would use these sets of formulas to come up with a sample size that we would need to be within 1 percentage point margin of error. So the way that this works is really just algebra. Talked about that. So confidence interval is always the mean plus or minus. What's the z term here? That's the table from the z. I mean, that's the table value from the z distribution. But yes, it's based on the alpha. It's based on the value that we need outside the tail. Okay. And then what's this term right here represent? Yeah, it's a little bit different in each situation, but yeah, it's based on the standard deviation. Remember we talked about what the hat meant last time? Right. Yeah, so it's an estimate of the standard deviation for the mean of x. Okay, so here it is. The error term is z times this, or the way we estimate it is using the standard deviation squared divided by n, take the square root of all that. That's in lots of the formula. The hat means that it's an estimate. So the we don't. This value is the standard deviation for the population.
Oh, okay.
We don't have the standard deviation for the population because it's unpractical to actually have that. We don't know what it is. And here we're assuming that we do have it, which was the way it was in a lot of the homework. And so we take that value, square it, and then divide it by n, take the square root. If we don't know it, there is the formula in your book. It's a similar formula. It's in the tables. Yeah, so table 8.4 has that formula. And it's almost the same, but we have the sample standard. We're using the sample standard deviation instead. And then what's that n minus, big N minus little n divided by n? Remember, that was the thing you asked me about. You said that maybe it went by another term in one of your other classes. What's that? Right. It's the population. It's the population total minus the sample size total divided by the population size. So it's the finite population correction factor or something like that. That's what that is. So you don't always need to use that unless it's greater than, unless that value works out to be greater than 0.5. All right. Finite population correction. Yeah, FPC. It's on the next page after 8.4. Okay. Great. So we can use the sample standard deviation. This one gives the population standard deviation, but we could use that if that's all we have, which happens a lot of times. So then we decide what error we can have. So whether it's 10, which means 90% confidence interval, 0.5, which would be 95% confidence interval, 0.1, which would be 90% confidence interval. So then taking this formula here and just adjusting it algebraically, we get this formula. So we're just solving for n. Okay? But the z that we fit in here, where do we get that z from? The z right here, where do we get that value from? The table, and that's determined by what we choose here. So that's why we have to choose this. And then so we need to know, in order for this formula to work, we need to know the z value,
Is it always going to be one of those three, like the 90, 95?
No, I mean you could make a different confidence interval. Like you could say, I just want to be 98% confident or 97% confident. It's just that those are the ones that are most often chosen: 90, 95, and 91. So in this case, we might not. So in order to solve this formula, we need to know something about the standard deviation, right? But we're trying to figure out how big a sample size we need, and so we may not have even done that yet. Well, in order to do this, and one reason why sometimes people don't do it, is because in order to even calculate this sample size selection, we actually have to take a sample. That's what this means. Okay, we don't know, we substitute a sample sigma. Sample sigma can be found by taking a preliminary sample. So it's still a sample, we're just taking it beforehand. Greater than 30, then we can continue with the random sample for the results of n. Okay? So in order to do this, it does say sample size selection, right? But it still involves a pre-sample, and so it really takes two samples to do this. And that's why sometimes it's called a two-stage sampling design. You take one sample to kind of feel out the population, figure out what your sample size needs to be, and then you take another sample. So if you know that you don't have enough resources to take a sample much over 30, like if this is a thing where it's going to take, you have to drive out in the woods and you're actually sampling something that takes a lot of effort, and you know that you're only going to be able to get about 30 samples, you wouldn't even do any of this because your sample size is going to be 30, and you don't need to do it twice. This is for like if you're going to do a big study and you're trying to decide if you need to take 1,000 samples or 5,000 samples. Then if you were trying to do that kind of thing, you'd go out and take a sample of 30, calculate this value, figure out what n had to be for your confidence interval, and then go do it. If you're only going to get 30 to 50 samples, just go get 30 to 50 samples. Don't go through the effort of doing this. Figure out what your confidence interval is after you did it. And if it's not enough, well, you didn't waste anything, except for, if there was never any possibility that you're going to collect 1,000 samples, you didn't really waste anything at all. You just found out that you can't answer the question with the samples that you did take. Anyway, so here's how you calculate it. The minimum number of samples we need to make an interval estimate of the population total within a tolerance level can also be determined. That's arranging the algebra a little bit different. We can isolate n, and we need to remember to use s, which we already said. Best to run a quick tab. Okay, and this is the last one. Okay, so this is the same test, but doing a sample size for a proportion. So the example I gave at the beginning, the proportion of people voting a certain way that's an example of a proportion. So what you need to do there is, I don't think I did, actually didn't think I explained this term very well, right? So we talked about the N, and we talked about the S on the previous slide. What's the E? The E here is within a certain amount of allowable error. So your error is the width of your confidence interval. So if you want that to be 1%, then your error would be 1 in this case. If you want your, here on these, if you want your error to be, let's say you're sampling the size of the length of a turtle and you want it to be within 2 centimeters, then your error is 2, you just keep it in. All right. Okay, so there are a few examples from the homework regarding this, as well as some examples in the book. Let's see. Let's first do one of these from the book. Let's do example of a sample size selection mean. It starts on the end of page 135, but it goes into page 136. Okay. So it's a very simple example. Suppose a preliminary sample of 30 households is drawn. S is calculated as 210. What's S again? Right. So the standard. What's that? Stamp, exactly. That's more precise. Okay, so we took a sample of 30 households. So N, we're going to say that is 30. And S is 210. So then we could plug in the values there. Now they're plugging in 50 there as E. Okay, yeah. Why did they plug in 50 there as E? I skipped over that one. On bottom of page 139 it says, Middletown planners wish to estimate the mean annual energy expenditures per household and be 90% confident. So we have to express a confidence before we do this, and that their estimate will be within $50 of the true population mean. So they're saying that it has to be within 90% confident and within 50. So what they're saying is that, let's go way back here. We still don't necessarily know the true, well, we're never going to know the true mean, but we're going to make an estimate of the mean. We don't know this value. This value is still unknown. But what we want to do is, what we're saying is we want to estimate that value and be within 50. So this needs to be 50 this direction, 50 that direction. And what we're saying is that the confidence means that 90% of the time that value is going to be within this limit. What size population, what size sample do we need? So then you just plug the numbers in. So this is going to be at the E that we want, which is 50. And the confidence interval is going to be 0.90. So I'll just say alpha is, actually it's usually a little a. Little a is 0.10. Okay? So the first thing we need to do is figure out Z based on the little a. What's the Z value for the little a? For a being 0.1. Look it up in the table. Of course, it's right there. Yep, it's 1.65. It is 1.65. Lots of times those values are actually, you can just memorize them, but So I'm looking at table A, and I'm looking at the Z value of 0.05 would be the one that you would want, or sorry, alpha value of 0.05. Oh wait, no, you'd want 0.45 on this table. It's kind of confusing. Remember which table is which, but this one you'd want 0.45. 0.450. The closest one there is actually, it is 1.65. So it's in the 1, 2, 3, 4, 5, 6th column, and it's 1.6. It says 0.4505. So that's what that would be. So the Z is 0.165. By the way, you, Catherine asked earlier, 90, 95, 99%. Those values are often used, right? And so sometimes people just memorize those. They're 1.65, and then 90 is, what is a 95% confidence interval? I forgot what the value is, because I don't have it memorized. But 99 is 1.97. So I forgot what the other one is. 1.7 something, I think. Okay, so we can calculate the confidence interval, the sample size as Z times the standard deviation divided by E, and then you need to square that whole thing. Oops, not. I'm just going to go like this. Equals this times this. Okay, so that's it. So what does this number represent? 48. Yes, that is the sample size you need to get the answer that you want. In other words, if you want to be within $50 and you want to be 90% confident, your sample size needs to be 48.
Oh wait, okay, was it 99 or 1%?
You got which table is that? Because that's the table I was just looking for.
8.3?
8.3?
So are we using 99?
90. This one we were using 90.
Oh, okay.
8.3, yes. So it's 1.65. 95 is 1.96. Huh. I was looking at 1.97. And then 1% is 2.58. Okay. So look, if we did want to do 95% confidence interval, we can multiply this by 1.96. And look at how many samples we need to get to a 95% confidence interval. Goes up. You'd expect that, right? Now look at what happens if we wanted to get within, if we wanted to get within $25 and be 90% confident, what do you think is going to happen?
The confidence interval is going to be small.
The confidence interval, yeah, well, we're forcing the confidence interval smaller. So what's going to happen with sample size? That's what's floating.
Bigger.
Yeah, sample size is going to we're going to need almost 300 to get the sample size smaller. I mean, to get the confidence interval smaller. 25, if we're going to get within 25, we're going to have to get almost 300 samples. All right, so going back to the original question, though. Whoops. redo. I'll just say equals this times this. 48, it's almost like, because we already, in order to get this information, we had to take a 30 size sample. So unfortunately, we almost like did extra effort for ourselves. So we just took a sample to figure out that we need a sample that's just barely larger in order to answer our question. Okay, so that's what I was kind of getting at, is that if you know that your sample size isn't going to get much larger than 30 to begin with, or you don't have the resources, then this is kind of a futile effort because you just made yourself do double work. Okay, so let's do, now that we've done that, if we go, because that answer was already given in the book. So let's try one a little bit harder. So we got our files here, chapter 8. I believe there were a few questions at the very end regarding that. Maybe there wasn't. Was there?
I don't think you had to estimate or
Estimate sample size? Okay. All right. Well. Okay. But we did leave it off on where you had to. What'd you say? Okay.
Yeah, I don't remember calculating or estimating sample size.
Okay, that's not on the.
So
That's,
we're trying to double check.
yeah. Okay. All right. Well, now you've seen an example, and not messed it up. We changed it up a bit.
Dr. Raver, that's what the question was. On number 7, on chapter 8.
Number 7.
Yeah, so you're estimating the average water usage?
Yes.
So we're not estimating sample size there, right? Because it's given to us?
From the 40. What? Sorry. What were you saying, Justin? Yeah, we have the luxury of actually knowing the population, so enable us to understand how reasonable our estimates from 40 household survey are. Yeah. So they sampled 40 residents. Let's.
But there's actually, I think there's actually more than 40 values.
This is the table, the data table, right? All right. Let's look at that. Maybe this can be our other example of one that we do. Okay. So that's chapter 8. We're talking about this question right here. No, this question right here. All right.
Yeah, there's actually 47. The sample size is actually 47.
Yeah, so we use 47. Okay, workbook data. Did you already work out that problem?
I tried to do that.
Because that one wasn't, that one's not stratified, that's random sample, it looked like, right?
Well, so in the paragraph, it says it's a proportional stratified sample. So you use the formulas in table 8.5.
Okay. What's that?
Yeah, but then at the top it says part 3. It says random the samples. But then in the paragraph, it tells you it's a proportional stratified sample.
Yeah, no, you're right. It does say that in the, and the fact that, does it say proportional stratify?
In the
Okay,
paragraph.
yeah, so with proportional stratified samples, let me make sure I know what I'm talking about here. So when we go back up to sampling, which one did you end up using? A5 or A4?
I think I used H5.
Okay. I mean, that's probably fine. It would be interesting to actually to crunch the numbers, but my guess is that in a proportional sample, the number is going to be pretty similar. The actual confidence interval is going to be pretty similar as to what would be in random, as long as the samples are proportional. So because let's say we took 100 random samples, right? We took 100 random samples just for fun, okay? We took 100 random samples and we had 3 different categories of things. If we took 100 random samples without caring about which category each one fell in, you would expect that those 100 random samples, if we put them all together, it would be fairly proportional if it truly was random. See what I'm saying?
Yeah.
And so that's why I'm saying that if it is a proportional stratified sample, there's going to be less. You're introducing less bias than if it was a disproportional sample, and therefore the numbers should work out pretty similar.
So for this example, like the proportion, it gives you apartments, condos, and townhouses, and it gives you like the population numbers. Then the sample that it gives you, it makes you have to calculate the proportion, and those are similar to the population proportion. So if you use either formula, you would get a similar answer.
Right. Yeah, that's what I'm trying to say. Is that what is the? Did you calculate the proportion in each one?
So apartments is 15
And so you're saying it's 15%.
of the
So
sample.
it's the total number of samples divided by the number of samples in the apartments divided by the total number of samples. Makes sense. Yes, 1, 2, 3, 4, 5, 6, 7. And there actually are not 40, there's a few more. How many are there total?
47.
47. So it's 7 divided by 47. No, that's 7 divided by 47. That gives you, let's just go ahead and, I know you already did this one actually. So this gives you that's the proportion in your sample that were apartments. And how many residential condominiums were there? 26 divided by 47, and then there were more than
No,
that.
that's fine.
This is 26?
Yeah, so it's 26 townhouses and 14 condos.
Equals the sum of all those. So this one is 1, it should be, I'm just making sure. That's the sum of these. So of our sample, almost 15% were apartments, almost 30% were residential condominiums, and 55%, a little over 55%, were townhouses. Okay? So we need those numbers to feed into the confidence interval. It's the third formula in table 8.5, which is also given here. So this was the other thing that I was going to talk about, was the stratified sample. Because stratified sampling is not as, it's this formula right here. Stratified sampling, the formula isn't as, it's kind of a bigger formula. It has one of these things in it. What's this mean? Sum. Yeah. So what it's saying is that you have to sum these values for each step. And by the way, if you actually start this slideshow, those don't show up. It's just, it was hard to make those boxes don't mean anything is what I'm trying to say. So if I start this up, see how the box is right there. They don't mean anything. So this is the formula that's given. All right, so
Kind of off topic, but do you know how you get those symbols on the keyboard?
Like, where do you go to that?
yeah, so there's a equation. So this is equation tools. It's in there. So if you like insert a new equation, insert equation right there, and then symbol. So if I inserted a new equation right there, then it gives me all these tools. Like there's a square root symbol. If I want to, do integral, I wouldn't. This is all calculus, but I mean this is all not calculus in this case. But yeah, you've got one exponent. Anyway, they're all in there, so that's how you create those. It is, takes a little effort. It's not just like, bam, I just cut and pasted in there, it works. So sometimes you'll notice that in some of the slides, I just like took a picture of it and drew it on. Yeah. Seven. So you're saying if I go back to question 7, what isn't this? Okay. Okay, so the population size is the population size of the apartments. So that's this value right here, 100. So in this table, let's see if I can just. Yeah, so this will be 100. This will be 14. The sample mean is the mean of just this column. Let's calculate that real quick. So just this column right here. So the sample mean is equal to the mean or average of this. Oops. So that value right there, 95.57, is what goes right here in the sample mean. And then the sample standard deviation is standard dev of this column is 56.62. So that's that value right there. And then compare those to, well, it doesn't actually give you that, does it? That's the the sample mean, the sample standard deviation. You can do that for each of those. So you'd fill out that table like that. That'd be 7. And then, what's the estimated average water use per household for the city? Calculate the standard error of the mean and place a 90% confidence interval about the mean. So that's this line right here. So how would we get our sample size is really 47? Because it says 40, but I don't know why they didn't get that right. That's an error. I have to tell her, not here. She's talking about all the errors. All right, so sample 40 rather than say really sample 47. So, what are we trying to get? The average water usage per household. So what's the best point estimate of the average water sample per household? That's the easy part, right? How do we get this number right here? The best point estimate. In other words, it's I'll give you a hint. It's this right here, right? So the best point estimate is the sample mean. The best point estimate of the mean, the population mean, is the sample mean. So what's that value going to be? How do we calculate that from this data?
So you can't just average them all.
Yeah,
Right.
we can. We don't have to use the second formula until we calculate the confidence interval.
So you have to, can you average them all, or do you have to average them individually? Take the mean of
We're just going to average them all because that's the best estimate. We just average them all. There's no in formula 8.5, X bar is the sample mean. So we just average all of this column right here. So we take this value and we sample, we say equals the average, average of this column right here. I'm pretty sure that it's going to let me ignore those blanks. Did you calculate that out to be any different? 48.34. I don't have the key with me. So.
Calculated it using the formula, the best point estimate formula, and he makes it 5.
Where's the best point estimate formula?
It's
Oh.
the top for stratified samples.
Yeah, you're right, because this is a stratified sample. And you came up with 48.5? No.
42.79.
42.179, okay. All right, yeah. No, you're right, you should use that one. It's not clear to me in the question. Okay, the data did include a proportional stratified sample of homes based on blood type. So, yeah, we should use the one you said.
I think that's where my question was, because it says random samples.
It does, right here.
And then it says, so I did the first time I just like averaged all the means, and that's like 48.3 something. And then, oh no, I got 48.04 when I used the formula.
Yeah, I got 48.34.
So the answers are similar, but
But you said 42 was what you got
no,
before.
I actually lied. I
Okay.
got 48.04.
48.04 when you did the 8.5 table, and then what did you get the other time?
When I just averaged them all?
Yeah.
I got like 48.
Okay. So yeah, when you said 42, I got got discouraged, right? I thought, oh, that seems weird. Because these samples are so close to the true proportion, right? I thought that they should be pretty close, and they are. They're within the average water use per person is within 1 unit, whatever it's in, gallons. What is it in? It's in thousands of 10,000s of gallons, but it's still within one of those. It's 48 and 48. So let's calculate it both ways. After we already did it, we just calculated it just doing the straight average. Now let's calculate it using the formula because it is a stratified sample. All right? So with the formula, what we need to do is take, what does the big N, I'm looking at the formula 8.5. What does the big N mean? Right. So we're going to have one, this is going to equal 1 divided by N. What is big N? 691. 691. And then we need to, I'm just going to leave that term alone for a second. Okay, this is 1 over big N because we need that. Then we need the sum of N and then the sample mean. But it's big N, so we actually need to know how many there are of the total. So if we know that there are 100 properties in the city, we multiply 100 times X bar. What is X bar? It's the mean, but what mean? Is it the mean of, it's the sample mean, exactly. Did we calculate the sample mean yet? We did for this one, but we didn't for the other two. There's the sample mean. No, wait, that's the sample standard deviation, isn't it? No, that's the sample mean. Yep, okay. So that's the sample mean. So now we need to do that for the other two. So we could just say equals N times, and we can actually just plug in the formula here rather than calculating again. The average of this column, and then do it again, equals the N for townhouses times the average of this column. I'm still getting, average. Okay, so I have these three values. This is 1 over N, and then this is the three values I need to sum up. So I need to sum these values and multiply them by that. And that's going to give me the value that I want. What's that? Yes. Because that's the whoops. I forgot to put I sum these guys and then I multiply it by this guy. Is that the value you got? Because it's a little different, I think. I wonder if, maybe I didn't get one of the values or something. That's the right. But it's still pretty close.
So that's all your in-time RX values, right? So.
Wait a second here. I did it wrong. I mean, I just used the wrong values on the second one here. See what I did? I did the townhouses twice. But I used the N, the right N, but I used the townhouses. There we go. So now I got the same thing you did probably within, right after, you said 0.480 something. I know you did.
48.04.
Okay.
Yeah, yes.
Okay, that's what I got. So this is assuming that you took a random sample, and this is a stratified sample. Okay? We actually did a stratified sample, so we should have used that. But our stratified sample, we already verified our stratified sample was really close to being proportional. It was almost was proportional. So these numbers, 0.57, we had 0.55. And so you'd expect those to be close. Yes, that's the best point estimate. So that would go right here, right? The best point estimate. From the 48.4? How did I get that, or how did I? This one? Okay. These, each one of these, so I'll label these. Oh, yeah, okay. So this is townhouses. And then this is whatever, condos. Is it condos? No, yeah. And then this is apartments. Does everybody in this town live in some form of attached housing, I guess? Nobody lives in standalone houses, I guess. Very atypical of around here, at least. Okay. So yeah, this is the point estimate. So if it was a random sample, you could just use this number. This is just the sample mean. But since it was a stratified sample, use this number. Okay, so how do we calculate the confidence interval? For that, I am going to calculate the standard deviation. I haven't done that for each one of these. So I'm going to calculate, that's going to be the standard deviation, equals standard dev of this column, just because I want to have that as a number. And then this will be the standard deviation of this column. So now I have the three standard deviations.
Should we be using the standard deviation, because I have standard deviation .s and .p?
Yes. So one of those is the same. Oh yeah, because the calculates the standard deviation based on the entire population, or based on the sample. So I guess technically it's a sample standard deviation. So I wonder which one the other one does. Do you know what the difference? So that's okay. Good. That's the same thing.
Yeah, that's.
What's the difference mathematically between .s and .p? Do you remember? Yes. So .s is n minus 1, and .p is divided by n. So it looks like by default the one that's not either one is the right one, the one that we want. So see how they're. So Ashley's question is, standard deviation .p is not the one you want. You want standard deviation .s, or this just plain old SDDev, which is a little exclamation point there. That's telling you that they want to get rid of it. It's not supported. It's been superseded by this one. But since I'm older, I've used Excel a long time, that's the one I do. Right? Because That's the one I learned. But now they've got a newer one in the, maybe it might even tell us. So, yes. So before Excel 2007, that was what they called it. After Excel 2007, like 11 years ago, they switched over to using, but they keep it in there in case somebody has an old spreadsheet that they open. All right, that's just an explanation of why that's there. So we calculated all of those standard deviations. So now we need to feed it into this formula, which is a little bit big, but we can do it. We've got this value. I'm going to copy that value over. Actually, I'm going to copy it all the way over here, this column. Okay, this one needs to be 691 times 691. Okay. Right? 1 over n squared. I'm getting a value of 1. That's why. There we go. Now I get a really, really, really small number, which is what I expected. Okay? All right, so I need that number, and then I need the 3. So every time you see a sum like this in a formula, that means that you're going to have to do that however many times there is. And in our case, there's 3. There's 3 times. There's 3 different strata. So if you were calculating this for something where you had like 10 strata, it would be awfully complicated. It would be more complicated. I mean, you could still do it. I'd probably write a program at that point to do it. But we've got our 3 columns right here. We want to plug the rest of everything on the other side of the sum into it. So basically, we have to multiply n squared. And we have to multiply that by the standard deviation divided by n. Standard deviation squared divided by n. We have to multiply that by the finite population corrected factor. And in our case, we probably should use the finite population corrected factor. I mean, we could calculate to see if we needed to use it or not. But our population sizes are so small, okay, that we probably are going to run up against that. Okay, so the first one is going to be equal to n squared. I'm actually just going to put n squared right here. Equals 691 times 691, because that's a constant. That's going to be in all 3. Okay. So I'm going to say equals that times the standard deviation squared. So I'm going to go up here. That's this one. Times F16 divided by n, which is, what's the little n? I don't think we stored it anywhere, but it's 1, 2, 3, 4, 5, 6, 7. All right, times the finite population corrective factor, which is going to be n, which is 691. No, sorry. We don't use 691. I messed up. So I use 691 here, and I use 691 here. That's not right. What population n should I be using? Not 7 is the little n that I should be using. But what population? I'm just dealing with apartments.
47.
Is that how many there are? No, it's the population. It's the population big N, so it's 100. I did that right on the other one, right? Yeah, I did that right on the other one, but not on this one. So this is 100 minus 14 divided by 14. Or sorry, divided by 100, because it's a big N. I'm going to make sure that this gets done first. Okay, so it should look like that. this number right here actually gets changed. So it's 100 times 100. So this is the N for the group. That's what it means when it says NI. See how it says NI in the formula? That's what that means. I means for just that group. So this is 196 and 395. 196 times 196 and then equals 395 times 395. So I'm going to fill this down, but each time I'm going to change to, this one's going to be F31. 31. How many samples were there of there's 195 actual, right? 196. How many samples were there of condos? Again, you're the one that told me last time, actually.
Single condos, 14.
No, that was the apartments.
26? No, condos is 14. Apartments is 7. And townhouses is
yeah. Boy, I'm getting confused. So this is 14, you said? So back up here, this would be 7. So messed up.
So, yeah, and the table in the, like, the table in the homework is not in the same order as the table in the data. You know,
So I'm just calculating the right side of that formula there, and big N is 100. There's 100 actual apartments. We sampled 7 apartments. This one, there's 195 condos, or 196 condos, and we sampled 14 of them. That's why we put 196 and 14 in there. Oh, and we also need to put 14 there. $196, and then there's 395. How many did we sample of this? You said it was 20 something, right?
no.
26 townhouses, and that one's in 58. That's that one. Okay. So E64 is just the big N squared. Now, the big N squared, it is because it's NI, it is not 691, which is all of the N's. It's just NI, which means it's just for that group, just for that strata, is what we should say. So now we've got all 3 of these values. And now we need to multiply. First we need to sum these up and then multiply with that. Because this is 1 over N squared. So we go equals sum of all these guys. What are each of these numbers? These are it's all of this stuff, and then now we're summing it. So we did it 3 times. 1, we did this. So we did this for the first strata, this for the second strata, this for the third strata, and it says we're supposed to sum it 1. And then we multiply. Oh, and then what we're doing now is we're multiplying them all by 1 over. See, this whole term is 1 over N2, which is 691. So when we hit enter, okay, then what do we need to do next? So we've just done everything under this little, well, the square root sign. So we need to take the square root. We've done everything under that square root sign. So we take that value and we square root it. Okay. So now we have the square root of that value. And we need to multiply it by z. Where do we get the z value? Let's go look over here. 90% confidence interval. So what's the 90% confidence interval? That's the one we already did. 1.6 something? 1.65. So equals 1.65 times this. Right? Okay, how do we get a confidence interval from that? Yeah, to the point estimate, which is this one in this case. So the upper bound would be this, equals this plus this is the upper bound. Equals this minus this is the lower bound. So our confidence interval, our point estimate is 48. It's in 10,000 gallons. The average amount of water usage is 480,000 gallons. This is per year, per household. Okay, so it's per household. So the average estimated water usage per household for the city, we're estimating that at 48. You add 1, 2, 3, 4 zeros. So it's 48, 48, 0, 0, 0, 0. Yeah, that's 480,000. So we're estimating that the water usage is going to be 480,000, but it could be as high as 569,000, or as low as 391,000. What's that? Because the units here are in 10,000 gallons. Total water use of 10,000s of gallons. So I just multiplied this by 10,000. So I could go equals this times 10. No, it's thousands, right? You're right, it's only 48,000. It's not. I thought I was seeing an extra zero. I thought it was in 10,000s of gallons. But it's in thousands of gallons. So it's only 48,000. Just pretend that's a common,
Did you divide by n squared before you put the square root?
Well, I multiplied by 1 over n. 1 over n squared. Right here is where because F61. Yes, so you could divide by n squared, right? But this is the sum, and then this is dividing by n squared, or 1 over n squared. Multiplied by 1. So I multiplied by it right there. Did you get a different number?
I got 8.42 for standard error.
For this number?
Yeah.
And then,
And then the confidence interval I got 13.8.
okay, let's see, 14, 26. Those numbers look right. What about, do you have any of your intermediate steps?
I think that I didn't account for it being in
Oh, okay, so you use 697?
back and,
Okay.
Will you post this Excel?
Yeah, I'm going to save it right now so I don't lose it. Yes, yeah, so the confidence interval is, you can, I would probably write it, in here, I'd probably write it as 56.9, or sorry, 39.16 through 56.292. That's the confidence interval. The confidence interval is an interval, so it's always two numbers. All right, so we did an example of one of the, and it's actually the one I was thinking of doing because the other one, that's proportion. The other one before it, I guess, is based, well, that doesn't actually have you calculate, oh yeah, you have to calculate the confidence interval. But that one requires that you've already done 7, so I don't have that written out. Yes, Justin. There are 1,382 properties that are either apartments, townhouses. Because we got 1,000. Yet, so no, that's not right. The 1,382, that's not correct. I mean, if you did use that, that'd be okay, but I wouldn't take off points because it says it in the book. But what's changing here is that you're estimating the total water usage, not the average water usage. That's what's changing. Yeah. Unless there's there's not a different sheet, right? That's the only sheet. That's the only sheet. Yeah. So those values should be the same. I mean, it's the same data. The sample mean, the sample standard deviation, yes. The thing that's changing is the best point estimate. That are either apartments, townhouses, or residential condominiums. Does anybody else have that question?
So you're just using, like, for number 7, like the first part of part 3, you're using this table 8.5, part 1.
Right.
You know what you mean. And then the next one would be part 2, because it's the same total.
Yes, part 2, the total.
And
Right.
then- okay.
And you can actually reuse a number of your data, I mean your values that you calculated, because look, everything under that curve is the same except for you didn't multiply it by 1 divided by n. Everything under the square root symbol is the same except for you didn't multiply it by 1. So actually, we already calculated that. All we need to do is multiply, instead of multiplying it by 1 over n before we take the square root, we just take the square root. So going back here, so here we'd go SQRT of just this value, because it's just the sum of those 3. And then this would, it's really, really similar. Oh yeah, because that one's so small. No, That's the wrong value, because it's no longer times 0.61. So it's just it's the sum of all three of these equals the sum of all three of these guys, and you take the square root of that, SQRT of that. So that's that number, and then you multiply that by the z-score times equals this times 1.65. So that's 6138. But we also have to calculate the total, which we've already done too. You're just pulling out the end value. But this is the confidence interval. So you're going to estimate a total. Change these numbers up a little bit. So here's the point estimate, right? The point estimate was times C91. So if we just take this whole formula, oops, and then paste it here. So it's the exact same formula, but we don't multiply it by, we don't multiply it by 1 over n, which is dividing by n. So I'm going to call this x, that should say x bar in real life, but I don't have a way to do that real quick. Point estimate. So here is the mean water usage. Here's the point estimate for the total water usage. That's that value. And then we could take this number here and go plus or minus here to get the total water usage. The point I'm trying to get across right now is look at how similar part 1 and part 2 are in their formulas. There's really only one difference, and that is pulling out the dividing by n. So here's the upper and lower. It's this plus this equals this minus this. And I'll post that. So this is the point estimate. This is the estimated water usage plus or minus this value, which turns into those values. Because really, we might actually be more interested in how much total water we're going to use rather than the amount of water the average person uses. For totally different purposes. We might be wanting to report to somebody, hey, the average person uses this in water in our city, to help them kind of maybe as a public service campaign to lower water usage. This number, we might be more interested in budgeting. How much water are we going to use? That's the estimate there. That's why you have both of those. And then I'll leave you guys to do this, but this is going to be the proportion of residents in favor of the proposed legislation. It's the same data, but now you're going to be looking at this column, and you're going to be using the formulas from part 3. The finite population corrective factor is going to be the same, though. Remember to use NI, whether it's big N or little n, use NI. So how are you going to calculate the proportions of I? Well, the proportions of I are just going to be from this. And it actually doesn't matter if you use P or 1 minus P as long as you're consistent. Here, the proportion is, which one is it? Did that tell us? In favor, okay? So the proportion in favor is 2 divided by 7. That's the proportion in favor, 2 divided by 7. The proportion here is just add up all the yeses, divide them by, was it 14? All right, so that's how you do that one. Okay. Let's move on to the next chapter. And luckily, the next chapter does build on the previous chapter a fair bit. Okay. What I want to do. So here is chapter 9. Download this guy. Okay, so this is, we moved on into a whole new section in the book, but we moved on to a whole new section in the book, but it's like we've been building up to this. And so we talked today and last week about confidence intervals, but really this is the next step in the process, because we're going to take those same concepts that relate to whether or not something is a true population mean is within a certain confidence interval, and say, instead of that, we're going to say, well, what's the probability that these two samples came from the same population? Or what's the probability that this sample belongs to a population? So that's what today's lecture really boils down to. We refer to that sometimes as classical hypothesis testing, and p-value hypothesis testing is basically coming up with a p-value to determine what's the probability that one sample is derived from a hypothesis. I mean, from a population. We're also going to look at the difference in means versus the difference in proportions, because we've been doing that all the way along, looking at means versus proportions. And then finally, talk about a few issues in inferential testing, which we might postpone to next week, depending on how much time this takes. Okay. So, hypothesis is simply a claim about a population that can be put to the test by drawing a random sample. So, making a claim about a population is something like turtles in this population have, adult turtles in this population, have a shell size that's above 15 centimeters. An average shell size above 15 centimeters. That's an example of a claim. So, making statements regarding an unknown population parameters is part of hypothesis testing. Sometimes we use them to refine spatial models, and sometimes we use them to help us to develop laws or theories. I said laws and theories, either way. But if we test a hypothesis a number of times, and we confirm our hypothesis, then we can develop a law or a theory based on that hypothesis. That's actually what the term inference means. So we can, if this is true, we can infer that it's true for the population. Okay, so a properly created sample is essential to inferential statistics. Since we're relying on testing, we need our samples to meet all the criteria that we talked about back when we talked about sampling last week. So here are the steps. First, we need to state what we call a null hypothesis. We already said the hypothesis is a claim regarding a population. Specifically here, a null hypothesis is a statement regarding the value of an unknown parameter. So usually it doesn't apply any association between explanatory and response variables. So it's not saying this happens because of that. We're just stating a hypothesis. The alternative hypothesis is the contradictory hypothesis to the null hypothesis. So in my example with the turtle shells, if I said that adult turtles have an average shell size, this is a tongue twister, above 14 centimeters, then the null hypothesis would be that they don't, or that it's below 14 centimeters. Let's see. Yeah, so I actually stated it as 14 or larger.
Oh, okay.
Yeah. Above 14 would be 14 or larger. So I test whether or not it's below 14 as the test. Okay, so I calculated, I select the test statistic, and then the test statistic is the mean or the proportion that I'm trying to test. So it's going to test between the null and the alternative hypothesis. So it's average cell size in my scenario. Now what if I get a value from my sample of 13.8? Can I reject my null hypothesis outright? No. That's what we're going to talk about today. I have to determine if my confidence interval basically spans the true value of the average cell size. In other words, it may be that if my sample size was too small, or if there was a lot of variability in the population, that using statistics, just because I got 13.8 or 13.9, it doesn't mean that the true average in the population isn't a little bit higher. Okay? So that's where when we select the rejection criteria, we have to do the same exercise where we come up with an alpha, an amount of uncertainty that we're comfortable enough with, and then see if the true mean could fall within that range. Okay? So the value of the test statistic in which we reject the null or the alternative hypothesis, and then we go ahead and calculate the test statistic, and we compare how close the test statistic was to the rejection criteria, if it's depending on the direction, if it's greater than or less than, then we say didn't work. So then we make our decision regarding the hypothesis. So that's the steps there. So oftentimes in notation, we write the null hypothesis using this H naught is the notation there. That's the notation for the null hypothesis, which is based on one or more population parameters. And the alternative hypothesis, HA, is how we usually notate that. And the null hypothesis and the alternative hypothesis need to be mutually exclusive. I guess I'll put that down here. But that's really important. They can't like overlap. One or the other is true. So the true population mean of the turtle shell example, we're either saying it's greater than 14 or it's not greater than 14, which would be less than 14. Okay? So sometimes we might use one of the ones I just said, using greater than or less than. Sometimes we might say it's equal to. Okay, the average turtle shell size is 14. Okay, or is about 14. That's an example of a null hypothesis, and an alternative hypothesis is it's not 14. So is not. We can also do greater than, less than. So we call that a two-sided test when we just say is or is not, because we're looking at is it outside the confidence interval on this side and that side, or is it outside the confidence interval just on one side? That's called a one-sided test. So if we put a direction to it, is it less than this or is it greater than this? That's a one-sided test. If we're just saying it's not this, that's a two-sided test. Refer to it as a two-sided test. And the reason that that's important is that that area that's under the curve, we only have to look at one side under the curve. All right. In order to progress here in this discussion, we are going to talk a little bit about the types of errors that could happen. Because if we have a null and an alternative hypothesis, we could choose, and we could find out through our study that the null hypothesis is correct. Technically, we say we're going to accept the null hypothesis because we don't know with 100% certainty it's correct. We're using statistics. So we could accept the null hypothesis. If that's the correct decision, that's good. We've accepted the null hypothesis, and it is the correct decision. That's one way to make a correct decision. The other way to make the correct decision is to reject the null hypothesis. In other words, say that the turtle shells are less than 14 centimeters on average, and it is the correct decision. In reality, turtle shells in the population really are less than that. That's also a correct decision. So these are both correct decisions. We can actually state the probability of either of these things. This didn't work out very well. This should actually be under here. So the probability of the null hypothesis being correct and getting that is 1 minus the alpha that we choose. So, if we choose, alpha is just 1 minus the confidence level. So that's like 90. If we chose 90%, this would be 90%. And then if we make an incorrect decision, those are on the other side. So we may accept the null hypothesis, but it may in fact be wrong. Well, that probability is expressed as beta. Okay. Yeah, I guess there is a table in your book called 9.2, and I've flipped it, but I flipped it across, so it's the same. It's the same table. It's just expressed a little bit differently. Right. So what we're usually concerned about is if we make a mistake, if we make an incorrect decision. So the probability of a type 1 error is alpha, which is so if we use a 90% confidence interval, that's 10%. If you use 99% confidence interval, that's 1%. All right. Now the value for a type 2 error is the probability that we is the probability, that's this, oh no, that's type 2 error. That's the one I already went over. No, I just went over that one. The probability of alpha. The probability of type 2 error when we accept the null hypothesis when it shouldn't, that probability is beta. All right. So the trick here is to balance those two as well as you can. All right. Now today we're actually not going to talk about all of these. We're going to talk about a one sample Z and T test, and then the one sample proportion test. But over the next few weeks, we'll fill in the rest of these. They're all for different purposes. We have this. I just got off Wikipedia. There's a bunch of symbols. Yeah.
Are one of those the same as what's a critical value?
The critical value is yes. So one of them is the same as critical value. One of the rejection criteria is the critical value. It's the value that you pull off the z-table, and it's, so the curve represents a real distribution, right? With a real mean, and the numbers along that line represent real things. In my example I keep going back to, it's tortoise shells in centimeters, right? Now, the z-value represents the distance in standard deviations away from the mean. The critical value is the actual value, in this case it'd be centimeters, that's at that z-value. That's what a critical value is, the actual value that you calculate. All right, so just like with confidence intervals, the first thing that we need to do is select a level of significance. If we want to have only a 5% probability of rejecting H dot if it's really true, then we say our significance level is 5%. Okay. Now, what we do if it's 5%, when we actually go to calculate our critical value, 5% means that we want to have a 5% outside of this value. And so we're going to actually end up with two critical values if it's a non-directional hypothesis. And the area under the curve is going to be half of 5%. 0.25 is half of 5%. Now if it's one-tailed, in other words, if we're only going to say it's above a certain amount, or less than a certain amount if it was on this side, then we need 5% under the curve. And our critical value is going to be a 1.64, whereas here, it doesn't show this, but our critical value, it did show it, is 1.96. So these are both 5% probabilities, but this is a one-tailed, and this is a two-tailed scenario.
Okay, so it's two-tailed makes sense to split it between.
Yeah, you split it on both sides.
So if it's 90 or like, if it's 90, I would say, 1.05%.
Yep, 0.05 on each side, or just 5 on one side. And so the idea here is that you calculate your, so we're going to do this one today. Talk about this, okay? You calculate your values based on a one sampled z-test. You plug in, you look at a z-table. So there's the test statistic zoomed in. That's too hard to read on this slide. Here it is zoomed in. That's just test statistic that we're going to calculate. So z is going to equal x bar, which is what? Sample mean minus the mu of 0. So this is the hypothesized value. So in our case, if we went and calculated a sample mean, in my case, I gave that example of 13.8, and we knew that in reality, we were trying to test to see if it was different than 14. We put 14 here and 13.8 there. We divide that by the standard deviation divided by the square root of the event. What's this called again? S.
Standard error? Yeah.
Standard error. Yeah, that's right. Standard error. Okay. So, so when we reject the null hypothesis, we are implying that we're accepting the alternative hypothesis. All right. Let's see if we can get into a few examples. Talked about that a bit. So if I was trying to say that, if I was trying to, in my example with the turtle, if I was coming up with that, I'd calculate a z-value. When I calculated that z-value, I would then compare it to either these z values or this z value and see if it was different. So here I've got 1.64, it's directional. If I calculated a z value that was over here, then what I would say is that they didn't come from the same population. That population didn't, and I would reject the null hypothesis and say no, they're definitely smaller than 14 centimeters. So you fail to reject here in the center. That's what I'm trying to say. If it's outside, you can reject. In other words, if your z value that you calculate is out here, reject it. If it's in here, you accept it. You fail to reject it. All right, so your p-value is the smallest alpha the observed sample would reject HO. So the p-value is the area under that curve. Okay. Okay, so here's the steps. We're going to compute the exact p-value, compare to the predetermined alpha level. If the p-value is less than the predetermined alpha level, we reject the null hypothesis. Those results are statistically significant. If the p-value is greater than, we don't reject the null hypothesis. And results aren't statistically significant. Okay, how much time do we have? Oh, we got plenty of time. So I wanted to do an example at this point. So we're in, we're talking about the difference in tests here. Okay. I thought I marked which one of these I wanted to do. I guess I didn't. Okay, let's just do from the book the one sample difference of means test. Yep. So we're going to compare a random sample mean to a population mean for a difference. So kind of like my example with the turtles, but here in this example, we are we're going to calculate the test statistic. This is the example. Sorry about that. Okay, so in the example in the book, they're saying that the hypothesis is that the mean is 2,000. This is on page 143. And the alternative hypothesis is that the mean is not 2,000, so it's not directional. However, we're gonna look at both of them for fun. So the second alternative hypothesis is that the mean is less than 2,000 or that it's greater than 2,000. If it's got a greater than or a less than, then it's one tail. All right. Okay. So we have to plug our numbers into the test statistic. So that's step 2 is just determining whether or not it's which test statistic we're going to use, and we're going to use the one sampled difference in means test. All right. So Step 3, though, is calculating the significance level. That's where we choose what it's going to be. And let's choose an alpha. I'm going to go back to Excel here. We're going to choose an alpha of 0.5. It's going to be our alpha value. I'm going to write alpha. Okay. And then we're going to calculate our value based on this formula right here. So we're going to look. And the example from the book says that when we sampled this population where we expected a value of 2,000, in other words, we're saying that the national norm is 2,000. So that is the value that we're going to test against. So 2,000 is the mu value right here, this mu value. And then x is the sample mean that we got, which is 1,000. So I'm gonna say x bar and mu. I'll just write u. That's going to be 2,000. This is going to be 1810. The sample standard deviation is 196. Okay, that's the sample standard deviation. And n is 24. What do we need to watch out for when n's 24? Remember when we talked earlier, we haven't been hammering it too hard, but we use a different set of tables when n is less than 30, right? We use the t table. So we need to remember to use the t table and not the z table to find our values. Okay, so now we plug this into the formula. So that's going to be this minus that, okay, and then divided by 196 divided by SQRT, and select that. One more. I'm going to put some parentheses to make sure this is working right. Okay, so that's the value that I get. Negative. Oh, sorry. N is actually 25, but still, it's 1 minus. 24 is 1 minus n. So let me say 25 here, and then I change this to minus 1. I got a slightly different number than they did. 1810 minus 2,000. Divided by 196 divided by 24. I'm pretty sure my number's right, according to that.
Why do you do n minus 1 for that?
Oh, why do you do n minus 1? Yeah, you're right, because, well, this says n, not n minus 1. I mean, that is the formula from the book is n minus 1. Oh, if it's t, you use n minus 1. If it's a z-score, if it's over 30, you can use n. Because it's a t-score rule. I don't know. 1810, trying to figure out why my math is different. 1810 minus 2,000 is that. And then the denominator would be this, 196 divided by SQRT of this minus 1 equals this divided by this. Yeah, I mean, it's a whole lot of different rounding. Did anybody's book say something different? Is that an error that he might have corrected?
I got the negative 1.7.
4.7? Okay, well, I think that's the right number. So we can use that number, negative 4.749. And then, well, actually, I do like how they do it better. So look at step 4. Step 4 says that go look at what the value of t should, the cutoff value of t. It's kind of like the critical value, but it's for t, not for the actual number. So you go look at that. So for an alpha of 0.5 in the t-table books, the t-table for degrees of freedom 24 and for a level of confidence of, it'd be 0.95 is 2.06. Okay? That's what they got, 2.06. Now another way to get that is to go to the degrees of freedom 24 in the big T table and go all the way down until it gets to well, there isn't one that's at 0.4. Yeah, there's not one nice value, so it's easier actually on the other table. Besides, I don't know what area under the curve it's giving us in table C. Yeah, okay. Now what if it was directional? Would we still use would we still use 0.9 and get 2.06? Or 0.95 and use 2.06? If it was directional, and we had all of the value on one side, which value would we use? This is a little bit, I would say, first of all, why are we using the column that says 0.95?
That's our confidence.
Yeah, and specifically it's the alpha value that we chose. It's 1 minus the alpha value, right? Okay, but what if it was directional, which it wasn't? Which alpha value would we choose for a one-tailed? If our alpha value was still 0.5, okay, let me look at this. I'll show you what I'm talking about here. Let's go back to here. Okay. So we just did this exercise here, where we had 95 is under here, 2.5 is under here, and 2.5 is under there, right? Because we wanted to find this value, which on the z-table was 2.06. It was a little different than the z-table, okay? But what if this was the scenario, and we wanted 5 here? How do we get this z-value, or in our case, t-value? How do we get that? This is 95, right? But the way you look it up in the table is weird, because this is the point I'm trying to get across. This whole area under the curve is 95. But what we really want to get is this number, and in the table, it's always the middle, like kind of like the middle value, but it only reports this. So, if we want to get just a one-tailed, we need to change this from 95 to what value in order to get this value. So what we need to do is take alpha, double it, which would be 10%, and then subtract 90. I'm just saying, using this table for a one-tailed sample, for a one-tailed test, we would choose the 0.9 thing, go down to 24, and we get a value of 1.71 instead of 2.06. If it's one-tailed. We're not doing 90, we're doing 95. I wish I could show this diagram. Everybody look at this diagram at the bottom here. Okay? We're trying to find the critical t-value. Right? So that's this value at the bottom. And the confidence level is expressed as the area under the middle of the curve. But if we're not doing the middle of the curve, if we want just one side or the other, then the confidence level is actually, what we actually need to find is the area under the curve plus the little extra confidence on the one side. This is a harder concept to explain.
So in the diagram that's like here with the t-table, the white area on either side there, that
Yeah.
area would be 0.25.
In this, right.
If it were two-tailed.
And it is. This example is two-tailed.
And this table is giving us two-tailed values.
Two-tailed values, exactly.
Table to get one-tailed values.
To use that table to get one-tailed values, what you need to do, because what we need to do is find 0.5 over here, right, to get a one-tailed value,
Right.
right? And so what we need to do is look up, even though it's only one-tailed, we need to look up the value for 90 minus 0.5, or another way to say that is 90 minus 2 times r alpha. Or not 90, 1 minus 2 times r alpha. This should be 1. 2 times this. Because we need to look up 90 to get a one-tailed.
Because the total area we're looking for is going to be 0.5.
Right.
Or 0.05.
Because if we're looking at 0.5, the rest of this is going to be 95. But that doesn't, one-tailed doesn't exist in there, in the table.
So the table is just telling us the middle of the curve, so we need to think about how to find the middle of the curve.
Right. Yep. The table is just giving you the middle of the curve. So if it's a two-tailed sample, that's fine. And this one is a two-tailed sample. So we know our critical value is what, 2.06? And it's plus or minus 2.06. It's on both sides. And we calculated the value of negative 4.74. So it's way outside of that, right? Okay. So it's way outside of that. And therefore, if this value is greater than this value or less than this value, then we reject the null hypothesis.
So in this example, if it were one-tailed, and we were doing alpha with 10, we would just go to the 0.9 column and go down to where the 3.
Right.
And that's what you got.
And we get 1.7 something, right?
1.71.
That would be 1.71, okay? So let's just say that our sample standard deviation was way smaller. Let's show how that changes. So our sample standard deviation, we're going to bump it down to 100. Well, yeah, that'll make it even more. Sorry, that'll make it even more sure that we're different. Okay, let's bump it up to to 300. Go the other direction. That's still not. 196. Okay, let's make the X bar actually higher then. 1900. Okay, we're approaching it. Let's say our X bar was 1950. Yeah, okay. So if our sample mean was a lot closer to our true sample, we would get a value that was now we could say that the true sample and the true population mean was very close, and we wouldn't reject the null hypothesis. It could be that our sample really was a sample of the true population. That's what we're saying. Because this value is now within -2 to +2.06. Let's see if there's a value that would be 1930. Yeah, okay, so there's a value that would be. So if our sample mean was 1930 and we were looking for a directional mean, in other words, we were saying that the probability that our sample was less than the population mean. Now this number is within that range, but not within the second range. So if it was two-tailed, we would accept the null hypothesis, but if it was one-tailed, we would reject the null hypothesis here in this scenario, because this is just barely outside of -1.71 to +1.71. So we would reject it, but we would accept a two-tailed value. To get a two-tailed value? Yeah. I'm struggling with teaching it correctly. I think probably the best way to think about it is that it's symmetric, right? The distribution is symmetric. Okay? And so, because the distribution is symmetric, it's always telling you the value of the middle, the middle of the distribution. It's telling you that value, assuming that you're giving it this value here. Actually, what does it say? No, it does say, yeah, it says level of confidence. Yeah. So it's giving you the level of confidence, so that's that. So if your level of confidence is 90, then you've got 0.5 on each end. If your level of confidence is 95, you've got 0.25, it's actually 0.25, sorry, on each end, right? You got those on both ends. You come at these problems by this number. So you come up with that number first. So if you come up with that number and it's 0.5, you need to divide that number in half. And it's doing that math for you. It's dividing it in half. But if you only want one of the tails, you need to know that in order to get, because what you're really concerned about is the t-value or the z-value. That's right here. You need to take that number and say, oh, well, if the number in the middle was 90, then I'm going to have 5% left on this side. Or if the number was 95, I'm going to have 0.025 under the curve on that side. Yeah, overviews. I messed up both of those. So the steps in the t-test. Here, let's go back here. Yeah. One tail, two tail. Yeah. So all, that's right. They just eliminated one. So our degrees of freedom is 0.4. So it's 1.71. Remember what we came up with? Okay. So our t-table in the back of our book only has the t-tail column. Right. 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 Yeah, that's yeah. Degrees of freedom is always the sample size minus 1. Yeah, it's always n minus 1. So the way that you read this table is that, so in my example here, we actually chose the alpha of 0.25, so we need 2 there. And so if you go down on 0.25, you get 1.71 for 0.4. Or 0.25 two tails is 2.05 into 2.06. One of the things is that in a lot of these, it seems like not every statistics book, but so many statistics books have different tables, and you just need to become familiar with the table that you're using and understand what it's telling you. So for some reason, this book doesn't give one-tailed values anywhere. And so in order to get one-tailed values, you have to do a little bit of math. And all that is that you can use table T the way it stands for a two-tailed sample. If it's a one-tailed sample, instead of choosing your level of confidence, you're going to find the level of confidence yourself by taking your alpha value and doubling it and then subtracting 1 to use this table in this book. So if your alpha is 0.5 for one tail, you double that and you get 0.1, and then 0.1 minus 1 is 9. So you use the 0.9 column, even though that doesn't seem right, you use the 0.1 column, the 0.9 column. All right, so we did an example, and then the in both cases, remember that the small samples less than 30 use the t-test. The samples more than 30 use the z-test. These are just the numbers that are listed there. Okay. Here's a slide on it. The number of values in the final calculation statistics are free to vary. This is why we call them degrees of freedom. Okay. So the degrees of freedom are boils down to this sentence. Whenever a parameter must be estimated to calculate a test statistic, a degree of freedom is lost. And so we're estimating mean or proportion, and so because that is estimated, we're trying to estimate the mean or the proportion. That's one estimation that needs to happen, and so it's always n minus 1. Okay. Looks like we can get through the rest of this. I don't actually make any slides on the one sample difference in proportion, but the formula is even easier. It's just the proportion that you're testing against the population proportion divided by the standard deviation. So, yeah, that one's pretty straightforward. Okay, so here, oftentimes, I said GIS based here, and the book author uses the same terminology, but spatial data, whether or not it's GIS or not, often comes in totals. Like the census, for example, is already totals, right? I mean, the U.S. Census is everybody in the whole United States. Now, not every variable is like that. In fact, some of the more detailed variables like income and housing information are in fact samples. You only send those to every 20 or 30 people, 20 or 30 households. So those really are samples. But the population is a total. And sometimes you do get that in GIS data or in spatial data. You'll get values that seem to represent the entire population. And so how do you handle that? Well, one of those is that if you have reason to, particularly with like the example with census data, or even an evenly spaced grid, in reality, it really is a sample. It's not the whole population. You don't have everything. You just have an evenly spaced value that you got. There are values, in fact, in between those values that you didn't get. Or that's if it was a regular space grid. Or if it's census data, particularly if it's not just raw counts, if it's the housing or the income data, that's all really a sample. So you can treat it as such. And that's a valid way to do it, if you have reason to do that. Another thing that you could do is, if you really are dealing with something where you have the population, sometimes it's best to just ignore inferential statistics, not use them, and just calculate descriptive statistics. In other words, if you have the population value and you're trying to compare two counties, and you have every single, like, let's say your population is all of the Walmart stores in these two counties, and you're looking at their sales, okay? And you're saying the sales here compared to the sales here. Well, there's really no reason to calculate a confidence interval. Even if the sales are only $2 apart, you could say with confidence that the sales here were less than. Of course, what does that mean? I mean, if it's a big example, a big difference, then it can mean something. Right? Or you could calculate amount of money spent per person or something. See if people in this store spend more than people in that store. You don't need inferential statistics in those cases where it's not really a sample. Okay? So in some cases, if you have the population data, then you don't really need inferential statistics, and you can compare the descriptive statistics directly. Now, the final one here is oftentimes this is done if your data set is just too huge. Okay, like let's say it is an evenly spaced grid of elevation values or something, and you want to make some comparisons. Sometimes it's actually easier to take a sample of the larger data set and then use inferential statistics, just because computationally it's easier to do. And so you could compare, let's say you have some areas that were burned versus areas that weren't burned, and you're trying to calculate whether you're trying to just show, in our case, let's say you have two. Let's say you take a sample of each one, and you find out that you should expect to see an average of some habitat, some creature, 7 or 8 times per acre, something like that. You could then take a bunch of samples, even if you had the data for the entire region, the elevation data, and compare and see if it was different in higher elevations or lower elevations. Anyway, that was a pretty drawn out example, but the point here is that if your data set is really large, there's no reason to take it, that you can't take a sample of it and use inferential statistics rather than using the entire data set. So those are 3 ways of handling that problem of having what appears to be a total, a population value. Okay? So remember, we talked about a lot of these things last lecture, but these are important, particularly now as we get into inferential statistics. Remember that it's very important to define what your population is and understand that when you do one of these tests, you need to make inferences about the population, so you need to understand its limits, spatially and also population-wise. Then it's always helpful to investigate your variables through just calculating descriptive statistics, sample the data, choose a random sample if you can, and then make inferences based on the sample data. And then the last step here is to measure how well of an estimate that you created. Now, we've talked mostly about what's called parametric tests. In your book, we are going to talk a little bit more about non-parametric tests later in the course, but your book kind of just breezes by this for a second, so I thought I'd bring it up. A parametric test has assumptions about the underlying distributions of the population, and that is that they're either normal or they fit some other standard distribution, which works a lot of times. Usually, normal population is assumed. Non-parametric tests are suitable for any type of distribution, and oftentimes they work better with ordinal data or with ordinal data. So, like, let's just say you had a bunch of high, medium, and low values. That's what we mean by ordinal data. And with ordinal data, only non-parametric tests can be used. And so, although we're not going to talk about any of the specific tests today, know that there's a different class of tests that are valid when your population, is not normally distributed, or when you know that you're not dealing with numbers that can be added and subtracted. And those are called non-parametric tests. All right. It did the same thing, I think. I'm just going to let it see if it'll deal with that and come back after a few minutes. Anyway, we did get through all the material. I will keep that up. So only 7 is due tomorrow. 8 and 9 are both due next week. So as you work through those. I don't know. All right. Try to interrupt it and see. I didn't do anything. Ah.